Welcome back to Digital Replay, still in Unit 2, all about astronomy. Today we're talking about the story that light tells us. This is on pages 487 to 511 in our textbook. Now we can learn an awful lot about stars just by going outside and looking at them. And we learned in the last couple of labs that you can tell how far away a star is based on its parallax, or the amount of motion that it appears to have from one point in time to another. And in fact, we see that stars that are closer to us appear to move more against the background stars than stars that are farther away. Now this only works for nearby stars because the farther you get from us, the less you appear to move. It looks like you move less and less and less until at some point you don't really move very much at all. So now we can't use parallax to determine how far away you are. So how do we find out any information about far stars? How do we find out any information about them? For example, Betelgeuse. This star is in the constellation of Orion. It's actually the 9th brightest star in our night sky, the 2nd brightest in the constellation of Orion. And we know that this star is approximately 642.5 light years away, about 3.8 quadrillion miles, and yes, I said quadrillion. But how do we know that? This star is so far away that the light takes over 640 years to come from Betelgeuse to get to us. It's a long time. We've never been there, so how do we know so much about it? We can go on to Google and we can Google Betelgeuse, and all of this information comes up. Its distance to us, how massive is it, the radius of this star, the surface temperature, the coordinates. How do we know all of this? How could we possibly have all of this information for a star that's so far away? Well, it turns out that the answer has something to do with light. And in order to understand the answer, we have to understand a little bit about light. So let's start with light. Here I have a candle and a 100-watt light bulb. Sitting side by side, you could say that the light bulb is more luminous, it's brighter than the candle. Side by side, you see more light energy coming out of the light bulb than you do coming out of the candle. We call this its luminosity, or the power output of the thing. And in our case, in astronomy, we're talking about the power output of stars. So how bright is it really? How much light energy is leaving that object for real? Now, what if I took those two objects, that candle and that light bulb, but this time I separated them by a great distance? Watch what happens. As I move that light bulb further and further away from us, it appears dimmer. The candle stays the same brightness, it hasn't moved, but the light bulb now appears much more dim than the candle. The same amount of energy is still coming out of that light bulb. That is, its luminosity is still the same, but its apparent brightness, how bright it appears to be or looks to be, has changed. Now, it turns out that the apparent brightness of an object and its luminosity are related to the distance you travel. Let's take the example of a stage light here. The closer you are to the stage light, the brighter that light will be. As you move away from the stage light, it becomes much dimmer. It's more diffuse. It's spread out over a larger area, and the light isn't as intense. It's kind of like a sprinkler. If you think about a sprinkler, it's spraying water out from this one central location here. At this central location, we have the most concentrated amount of water right here, in this area right here. As we move away from the central location, the water droplets become farther apart. This is the same thing with light. As the light leaves the star, it spreads out and becomes more diffuse. It also appears to be dimmer. And it turns out that there's actually a relationship between the distance that the light has to travel and the apparent brightness of that light. And we did a lab where we measured the area of light of a flashlight at different distances, and what we found was this nice linear relationship. Now, scientists use a similar linear relationship called the inverse square law to relate apparent brightness, luminosity, and the square distance of light coming from stars. So we can measure the apparent brightness coming from a star using just a light meter. The luminosity is the power output of the star, and if we know that, we can actually calculate how far away that star is. Now wait a minute, how on earth would we know how much power output is coming from that star? Well, here's another cool trick. It turns out that stars twinkle. Some stars twinkle. Some of these far, far, far away stars are called Cepheid variable stars. That is, that they have a variable brightness. The apparent brightness from these stars changes in a cyclical pattern. We can look at these cyclical patterns and actually determine from these what is their period of time that it takes for that star to go from bright to dim back to bright again. So we can look at these periods, we can look at these stars, and we can actually take that information on a plot and find out how luminous that star really is. So let's take star D for an example. I want to calculate the period of this star, so I'm going to take from the first peak to the second peak, and that's approximately 11 days. So I come over to the second graph over here. I go to 11 on the x-axis, so I find 11 days, and I cross across horizontally to find out how luminous is this star. And I've now calculated the luminosity, or I've determined the luminosity of star D to be about 6,000. Whoa, crazy! So now if I know the brightness of this star, I know its luminosity, I can find out how far away is this star. It's fantastic. So the inverse square law is a relationship between the absolute brightness and the luminosity, which can then give you the information to tell you how far away that star is. So once again, the equation for the inverse square law was the apparent brightness equals the luminosity over 4 pi the distance squared. I'm never going to ask you to have this memorized. I just want you to understand what the relationship is and what it means. Now, what else can we tell from the light coming from stars? Well, you have a familiarity with light and some cool things that it does. And if I were to ask you about white light and what is it made out of, you might have a memory of learning that white light is made of many colors. You might have a memory of going outside on a rainy day and seeing a rainbow being projected onto the sky. That's because the light is being put through a prism, and when it goes through the other side, when it refracts out of the prism, we see it separated into its component lights, into its component wavelengths. So white light is made up of all of these colors over here, the rainbow of colors. You're familiar with that. Well, it turns out that if we excite gases, certain elements, if we excite the elements and get them really, really, really hot, really excited, they will emit light. Pretty cool. And we saw this in class and it was pretty amazing. So if we get these elements really excited, we heat them up or we burn them, we can see a particular color of light coming off of those elements. But even cooler than that, when we pass this light through a prism, it breaks up into different kinds of spectrum. So the rainbow coming from white light here, a continuous spectrum. Then we've got hydrogen. So the light coming from that hydrogen was separated into these colors. Not a continuous spectrum, just 2 or 3 little colors, little bands of color, of colored light. With neon, we saw lots of reds and oranges. See how this is not a continuous spectrum, but we're taking the light that is being burned or excited, we're breaking it into its component pieces. And you can see these bands of color coming off of it. It's really cool. Now it turns out that each element is like it has a chemical fingerprint. Like this light, these bands of color is exactly neon and nothing else. Neon is the only element that has this particular setup of bands of light. So this is like neon's chemical fingerprint, or elemental spectral fingerprint. These bands of color are exactly hydrogen. There is no other element that has these exact placements of these bands of color. So when we look at the light that's coming from, say, Betelgeuse, we can actually look for where those bands of color are missing. This is called an absorption spectra. We can look for where those bands of color are missing, and it will tell us what elements are making up this star. This star is made up of elements. Those elements are very hot, very excited, burning, and those elements then will show up in the spectra of that star. It's super cool. Now, the other thing that we can do with these chemical fingerprints, we can break it down, we can tell what is in that star. But the other thing we can do is we can look at the intensity of the light coming from that star. And we can look at the intensity at different wavelengths, at different colors of light. And we can look at that intensity and we can say, okay, this particular star has its highest peak of intensity at about 400 nanometers. What can I do with that? I can calculate the temperature of that star. So now we know what it's made out of, we know how far away it is, let's calculate the temperature. So I use this equation here, which is shown in your book, which is 2.9 times 10 to the 6th Kelvin nanometers, divided by lambda max. Our lambda max is where we had the maximum intensity of this star, which was at about 400 nanometers. I plug that into the equation, the 400 goes into lambda max, and I use my calculator. So I'm going to pull out my little calculator here and I'm going to plug this in. So 2.9 times 10, this is scientific notation, times 10 to the 6th divided by 400 nanometers. So this little e that I've typed in here, this just tells the calculator times 10 to the, and then I tell it which exponent it needs to do. So 2.9 times 10 to the 6th divided by 400, and I get 7,250. 7,250 Kelvin? And now we know the temperature of the star. Isn't that fantastic? Isn't that wild? So light can tell us a lot about stars. The light from stars can be used to determine how far it is to those stars, and it can also be used to examine what the stars are made of and what temperature they are. That's been today's digital replay. I hope it's been helpful. If you have questions, comment below, see me in class, or send me an email. We'll talk to you next time.